So here are some examples that are a little bit more difficult in using this definition of a derivative with limits. So here is a function. It's a fairly simple function, square root of x. And we want to find the derivative of it. Using this limit definition, not as easy as the previous examples we've seen. Most of the examples I gave you before were just polynomial functions, and those are the easiest ones to really work with. But we saw the computation getting harder and harder with each one we did. And so we'll look at this one. So what do we need? We need to know f of x plus delta x equals. In this case, it's going to be the square root of x plus delta x. We know what f of x equals. So if we use the definition of a derivative to be the limit as delta x goes to 0 of f of x plus delta x minus f of x all over delta x, we would get the limit as delta x goes to 0 of the square root of x plus delta x minus the square root of x all over delta x. Now the major problem here is that delta x is going to 0. We've seen this already. So what are we going to do? Well, here's a limit with square roots in it, where we have a problem where you can't just plug the value that delta x is approaching in, something we've seen in the last chapter. This is one we're going to try and rationalize. So if we multiply this by the conjugate of that numerator, so the square root of x plus delta x plus the square root of x. Now I have to do that top and bottom, so that I'm multiplying by 1. So that'll be x plus delta x plus square root of x there as well. If I multiply by that, what it'll allow me to do is in the numerator, when I multiply all this out, I can invoke the difference of squares formula, which is what we use in this rationalizing concept. In the denominator, I'll just have this times this, which is fine. We'll just leave that. And what do we end up with? Well, what we end up with is the limit as delta x goes to 0 of the square root of x plus delta x squared, because this times this, okay? So that'll end up giving me the square root of, I'll write it down, plus delta x squared, okay? Minus the square root of x squared. Remember, we're using the difference of squares formula. And what that'll do is that'll simplify those square roots. The next thing we're going to do is have the delta x times this denominator, and I'm not even going to multiply this out, I'll just leave it as is. So x plus delta x plus square root of x. Now what happens here is that since this is squared, the square root and this square will cancel, same thing here and here, and what it's going to leave me with is the limit as delta x goes to 0 of x plus delta x, that's what's left over here, minus here I'm going to have an x all over delta x times the square root of x plus delta x plus the square root of x. And seeing that we have an x and a minus x canceling, we're really just left with delta x here in the numerator. But guess what? That delta x and this delta x can cancel also after we cancel these two. And so then what do we really have? What we have is the limit as delta x goes to 0 of 1 over the square root of x plus delta x plus the square root of x. Okay, so that was the whole rationalizing thing. This is something we worked on in the last chapter when we talked about how we work with limits. The reason being so that we could do these types of limits. But now delta x is going to 0. Is that an issue? Is that a problem? Well, it actually isn't. Because if delta x goes to 0, this is going to 0. That's not going to make the whole denominator 0. It did here, but not now. And so what do we get when we let delta x go to 0? We get 1 over the square root of x plus the square root of x, which is really 1 over 2 square root of x. And so there's your derivative. Your derivative of the square root of x is 1 over 2 square root of x. Now, we have a second part to this question that says, okay, so find the slope of the function at, and I shouldn't say functions, function at 1, 1, 4, 2, and 0, 0. Okay? So the derivative gives us the slope. This is how we find the slope of f of x. So we want to do that at these three different points and see what we get. And so this is going to lead us to some more things we're going to talk about throughout the course of this semester. The big point of this one was this is a little bit harder derivative to find than some of the previous ones, but we're using a lot of the things we've already learned to get it done. So let's look at these 3 points. So we have our function, which is the square root of x. We have the derivative of that function, which is 1 over 2 square root of x. And so I want to look at it at 4, 2, find the slope at that point. 4, 2 is on this function. When I plug 4 in for x, I get 2 for my y. And so the derivative at 4, because we only need the x value to find the derivative, would be 1 over 2 times the square root of 4, which would be 1 over 4. So the slope of the tangent line is 1/4. Also, the slope of the graph, slope of the function at 4, 2 is 1/4. So here's a picture of the square root function. So this blue curve that goes right along here, that's the square root function. And so 4, 2 is sitting right here. And so if you look at this red dotted line, that is the tangent line to the graph at that location. And so what we're saying is that the slope right there is 1/4. Okay? So the slope of the tangent line is 1/4. The slope of the function right here is 1/4. All right, let's look at the next point, 1, 1. 1, 1 is also a point on this function. It's right here. When I plug 1 in for x, I get 1 for y. If I look at the derivative at 1, what do I get? Well, I get 1 over 2 times the square root of 1, which is going to give me 1/2. And so right here, the slope is 1/2. Here's this purple tangent line right here. That's a line that has now a slope of 1/2 instead of 1/4. So it's got a little bit steeper slope. It goes through this point right here. So the tangent line and the function have the exact same slope right there, and the slope is 1/2. All right, one more. How about 0, 0? 0, 0 is on this function, right? It's right there. If I find the derivative at 0, I have a problem because it's 1 over 2 square root of 0, which is 1 over 0, which is undefined. So the function exists here, but we're saying that there is no slope. The derivative is undefined there. So how could that be? Well, what's really happening is what we have is a vertical tangent line. This green dotted line right here is the tangent line. Vertical lines, we say, have an undefined slope. It's what we talked about when we were in algebra. We'll talk about it more as an infinite slope here in calculus. But what's really happening is that as I follow, here, let's erase all this. As I follow my function, which is, remember, it's that blue curve, as I follow it closer and closer and closer to 0, 0, the slope is going to get bigger and bigger. Here the slope was 1/4. Here the slope was 1/2. And as I keep looking at all these other points closer to 0, 0, the slope's going to get bigger and bigger and bigger. So we're going to have a tangent line that looks like that, a tangent line that looks like that, a tangent line that looks like that, till eventually the tangent line goes vertical right here at 0, 0. And so we're going to have to talk more about this idea of vertical tangent lines and the slope being undefined, but this is the start of it. I mean, the whole purpose of this question was to learn how to find the derivative of a little bit more complicated function, but nonetheless, this is an introduction to the sort of the visual of how these slopes play into the function themselves and what the tangent line looks like at these different points. So here's one more. Okay, and this one is a rational function, y equals 2 over t. So again, a little different. But we're going to use a lot of the same things that we've used throughout the previous chapter when we learned how to do limits. So what do we need? Well, what we need is the f of, we have variables t here, so t plus delta t. Okay, if you want to switch it to x's because it makes you feel better, we can do that too. So anyway, this would be 2 over t plus delta t. So if I want to find the derivative of this function, y equals, you can always write f of t equals. What we're going to do is we're going to look at the limit as delta t goes to 0. I'm just using t instead of x, of f of t plus delta t, which is 2 over t plus delta t, minus f of t, which is 2 over t, all over delta t. So again, the problem is delta t is going to 0. I can't just plug 0 in here and make 0 in the denominator, and we have all kinds of issues. So what we're going to do is instead, okay, this is t. Instead, what we're going to do is try and work with this fraction. So what I'm really going to do is I'm just going to combine these two fractions and actually subtract them, so find the common denominator, put them together, and work with it that way. So the common denominator there would be t times t plus delta t. So I have to multiply this numerator by an extra t. I have to multiply this other numerator by an extra t plus delta t. And I still have the whole thing over delta t. That's still there. Okay. So then I'll distribute this here and here. And what you're going to see is that some simplification is going to happen. So I have the limit as delta t goes to 0 of 2t. This will be a minus 2t. And this will be a minus 2 delta t. All over t times t plus delta t. And if you're dividing by this, this really actually multiplies in the denominator, so I'll just put it that way, delta t there. Okay? Why? Because you can think of this as over 1, and so you have a fraction divided by a fraction, so what do? You flip and multiply, so 1 over delta t is what you would multiply by, and you see it just multiplies into the denominator. All right, so what happens? 2t minus 2t, they cancel. And if they cancel, what happens now? What I'm left with is this over this denominator. Well, look, this delta t here is a factor, this delta t is a factor, so then they'll cancel. So what do I have? I have the limit as delta t goes to 0 of minus 2 over t times t plus delta t. All right, now is delta t going to 0 an issue now? Like, did we change this function to another function that we can work with? Delta t going to 0? Yeah. If delta t goes to 0, that doesn't make the whole denominator 0, it just makes that piece. We still have this left over, so what do we have? Minus 2 over t squared. Well, there's your derivative. That's the derivative of this function right here. So all we did is some basic algebra. Put these fractions together, right? Actually do this subtraction. Find a common denominator. Some stuff canceled out for us. Allowed us to cancel this delta t, which was really the issue. Once we canceled that delta t, we were able to do this limit. So this is just a short video of some more complicated examples than the basic ones I was giving you earlier, where they were primarily all just polynomial functions. But we can use this derivative definition, use it with limits, to do all kinds of functions. Okay. Now the problem is, this is going to start taking longer and longer the more complicated our functions are. So we're going to have to come up with better ways to find the derivative. And then we're going to spend quite a bit of time learning different ways to find derivatives without using this limit definition all the time.